Let's do vectors. Okay, so where we left off last time, we start by comparing vector quantities to scalar quantities. Okay, scalar quantities, they have just magnitude, not direction. Okay, so there are things like, we talked about temperature, mass, time elapsed, volume. These are all quantities that don't have a direction associated with them. So they're scalar quantities. Okay, vector quantities then, they have magnitude, they have amount, but they have an associated direction. So examples, force, momentum. Okay, but in terms of when we introduce vectors, the most common are displacement, and that's a change in position. So just the magnitude part of displacement then is a scalar, how far you go, distance. Okay? So displacement is distance along with the direction that you went in that distance, where distance is just a number, how far. And then velocity, similarly, is speed, how fast, but also in which direction. And so just the speed is a scalar. Just the speed is just the number, how fast. Okay, so that should make sense. That's kind of where we left off last time. Okay, so how do we represent them? Vectors are represented visually with arrows. Okay, so arrows represent vectors. Whatever way the arrow points, obviously it's the direction of the vector. Okay, that's the vector's direction. However the arrow points, but then the length of the arrow corresponds to magnitude. So if these all had the same units, clearly the second one has the greatest magnitude, and the third one is the shortest, or the least magnitude of the quantity. Okay, and then they all have a tip and a tail. Now, the vector doesn't have a tip and a tail. The representation of the arrow has the tail and the tip. Okay, so the vector, this is only a way to represent vectors, and so the arrow has a tail and a tip, and that is helpful when we start doing some computation to talk about those things. And then symbolically, you'll see in textbooks, you'll see it like bold, like a bold letter will represent a vector. But when you're writing, you can't write in bold, so you use a letter with an arrow over it, and that signifies a vector quantity. Okay? This is all intro stuff. Okay, so what about equal vectors? So since a vector has direction and magnitude, but it does not have distinct location. Okay, so let's see what we mean by that. So say 5 people, they start to move, but they move starting from different places, and they start at different times. But those 5 people all go the exact same distance, and they all head in the same direction. So it's kind of like this, if we put them on the coordinate plane. So they start at different times and places, but they all go the same distance in the same direction. So since that's what the vector's based on, those are all equal vectors. Those are all the same vector. So we could just call them all D. Okay? We just call them all D. They're all the exact same vector. So they're movable, right? As long as you keep the direction and the magnitude the same, you can move it anywhere you want it, and it's the same vector. It's an equal vector. So vectors are mobile, okay? Vectors are mobile. So what about adding? So here's 2 vectors. How do we add, and what does it mean to add vectors? So the representation is, since we can move it, so we move one so that they're tip to tail. So by moving it, it doesn't change the vector. And so what I'm showing here is adding B, starting at the tail of B, So the sum of the single vector results in the same outcome as applying the two vectors in succession. So what it's like is, say at the tail of B, that's where you live. That's your dorm room or your apartment. Okay? And first you're going to go to the MU. And then from the MU, you're going to go to class. And that's the A vector. It's going from the MU to class. So the sum of the two is like this phrase, how the crow flies, right? So it would be starting at where you live and going straight to class because the result is the same. Okay? So B plus A, the vector B plus A is as the crow would fly instead of taking the two different parts of the trip. So that should make sense as the sum. This is like the equivalent outcome in the end. You end up at the same place and the same starting point and end up in the same place. Okay, so what about if we did A plus B? What if we change the order of addition? So I can that's the exact same vector there, just moved over here. There's A. And now we're going to do tip to tail. Put the tail of B at the tip of A. And then A plus B would be, again, as the crow flies. And what do you notice about A plus B vector versus B plus A? It's the same vector, right? It's the same vector. Just like 3 plus 5 is the same as 5 plus 3, you can switch the order when you're adding vectors as well. You get the same resulting vector. Okay, any questions so far? All right, so vector components are, so that was just adding like as a picture. So what about actually quantifying this and putting some actual mathematics to this? So the way we do that is we express vectors as the changes of their horizontal and vertical components, or what's called the component representation of vectors. So here's the vector u, and here's the vector v. And so we want to kind of break down u into the part of u that is horizontal change, and the part of u that is vertical change. Okay, so the part of u that is horizontal change is 1 to the left, or -1. And then the part of u that is vertical change is what? Positive or negative, and what value? He said positive 2. Agree with that? Yeah, so it's really, so the sum, so just like we talked about vector addition, the sum of these two vectors is u. If you headed 1 to the left and 2 up, u would have the same overall effect as traversing those two vectors at the same time. But then it could also be a velocity vector, right? So if this is a speed in that direction, this is some speed in that direction, then there's components of that speed. The speed horizontally would be 1, and the speed simultaneously vertically would be 2. Okay? And so here's how we can represent that vector in what's called component form. Now notice that, so -1, 2 is not a point. It's not a location. What are those values? -1 and 2 represent changes, right? They represent how much change in the horizontal direction is represented by this vector, and 2 is how much change is represented by the vector in the vertical direction. So that's why there's this different symbol, these, I don't know what to call those, right? But it's not, don't confuse that with the point -1, 2, which is here. That's the point, and we could write it this way with parentheses, right? This is different now. This is saying a change of x and a change of y is what represents that vector. Add those two changes together, and you get the vector u. Oops. Shoot. Okay, so I was going to have you test you on this one. So what are the components? Could you write the components of v? Go. So write the components of v. Or write v in its component form. And so I gave you a really big hint. I didn't mean to do that. So what would V be in component form? What do you want? 4, -2. Nas, you agree with that? It's -2. Yeah. It's just not, it's not positioned right on the whole values, right? So it's just shifted. Yeah, so then writing V as its components, we'd write 4, -2. So here's why that's so important, because if we wanted to add U and V and get some kind of quantitative way of adding U plus V, we can't do it because they're in different directions, right? U is, they're kind of at an angle to one another, so how do you add those together? Well, if you break each of them down into horizontal and vertical, then you can combine apples and apples and oranges, right? So here are those two that we talked about. So let's move U, and we're going to add these together. So what addition am I showing? Am I showing U plus V, or am I showing V plus U? U plus V or V plus U am I showing here? No, but what am I? But I'm only representing in this picture one of those two. It's the same vector. Okay, I'm representing V plus U. You're right, they're the same vector, but in this picture is representing V plus U. Okay? And so what would you, so it's that. There's V plus U. It would be the single vector that would have the same result as applying vector V and then applying vector U. It's the single vector that does it in one step, or as the crow flies, right? As the crow flies. Straight line from start to end. So here's where those components really help, because now the 4 and the -1 are both x components, so they're apples to apples. We can add them together, and same with the y coordinates. So that vector then is 3, 0. And so now looking at how the image turned out, is it consistent with the vector 3, 0? Right? Because all of it is to the right, 3 units, and there's no vertical component. It's strictly a rightward vector with no vertical component. Making sense? Anybody have a question? Yes, sir, G.
If you flip them around, wouldn't the arrow be facing the other?
If you flipped them around, what do you want to flip around? Be more specific.
On the other side.
Yeah? So you want V to have its...
Or not me, you on the other side.
You put U here?
Yeah.
Okay.
And wouldn't the arrow be going to the left?
All right, so then I'll just sketch that on here. Good question. So U.
Then there needs to be.
So then now am I showing U plus V or V plus U? Now I'm showing U plus V. So here's our starting point, and where do we end up? Here's our finishing point. So which way? Do you see? What vector would start U here, start there, and end there? It'd still be going right. So the start is here. So our journey here is U and then V. So the sum is the single vector that accomplishes the same thing, that starts us here and ends us there. So it's to the right. Do you see? Is it better? Yeah. Yeah, so the vector sum is the single vector that accomplishes the same result as applying vectors in succession. And so there's our start, and there's our end. So we could go this way, U plus V, or just, it's the same as that. Yeah, Taylor.
How do you know which direction goes V plus U? How do you know it's V plus U?
I just made that up.
Okay.
Yeah, I just said, hey, let's add V and U together, so, as an example. Yeah. Nice. Okay, yeah. That was just, yeah. Okay, so we talked earlier that the length of the arrow, that represents the magnitude of the vector. So I want you to find the magnitude of each of these vectors. And so this is the notation for magnitude. It's like absolute value. You also see it with double bars sometimes. So it's the same thing. You'll also see it this way. means the same thing. So sometimes in some contexts they use single bars, sometimes they use double bars, but it all means the magnitude or just the amount, not the direction of the vector, and that's represented by the length of your arrow. So find those three magnitudes. Go. Taylor, down here. Any ideas?
Well, the only direction I went first was I tried to find like they're just a squared plus b squared, but I don't think that's correct.
So let me move you down here. Okay, so here's you again. Same vector, just different location. We're cool with that. How are we going to find the length of that? Yeah, I think you were onto something there. Yeah.
We have
Sure.
what's it called? I forget what they're called.
Components?
Yeah, the components for it. So it would be, for you, it would be go over -1,
Yep.
and then you go up 2,
Yep.
and then basically you just solve for the hypotenuse.
Yeah, so these components along with your vector make a right triangle, right? And so you had it. Yeah. So what will it be? It would be the square root of 1 squared plus 2 squared. So this is -1. I'm just writing the length of it as 1. Okay, and that one is square root of 5. So if that were a velocity vector, what would the square root of 5 mean in that constant? So if this is a velocity vector, then that number square root of 5 would be what? Distance traveled. Is it distance traveled? That's a velocity vector. The magnitude of velocity is not distance traveled. Velocity. It's speed, okay? It's the speed, so how fast, right? So the way it points is the direction. The magnitude would be how fast, if this is velocity. So that would be velocity. Okay, square root of v. What do you want? How'd you get that?
I did the square root of the 2 squared plus 4 squared.
Okay, so we can make a triangle out of that, and you down 2 over 4, and you did the square root of 2 squared plus 4 squared for vector v, and you got square root of 20. Does it make sense? How about magnitude of v plus u? Magnitude of v plus u. Don't do what you don't need to do, right? What's the magnitude of that? How long is that vector? Just 3, right? So when it's horizontal like that, yeah, you could, follow this kind of formula we ended up with the Pythagorean, but it's just 3 long, right? It's just 3 to the right, and you're done. Okay. Okay, so that's the nuts and bolts, so we can start solving some problems now. Any questions on that? So let's do this problem here. Force example. So force vectors A and B are applied at the origin, as shown. Find the component representations of each vector. That's problem 1. So number 1, you're going to find the component representation of each vector. And then 2, we're going to find a vector that gives the total resultant force at the point. So when you, maybe this is the ground, you got two ropes attached to the ground, and this is showing exactly how those ropes are pulling at that point. So there's a resultant single force that is comprised of those together. All right, so, and then we talked about component form, and now there's this other form called polar form, which is the way that these vectors are given. These vectors are given in polar form. We don't have the components. What we have is we have the magnitude of each vector and the direction as indicated by an angle. Okay, so that's what's called polar form. And we know what the component form is. Component form is the change in, so here, we can use our delta notation here to mean. Component form is change in x, change in y, the vector. So now, you've got a nice problem here to work on. Think of it as studying for your final exam. So everyone's working hard, and we'll regroup in a couple minutes. See what you can come up with.
Do you want me to skip my exams? So there. Got to be in my bags. What's your last name? No. That was yours. That was yours. What do you mean, Mouse?
I was confused.
Okay, how do we do? Let's see. How about Jimmy? Did you get it? Any progress? What's that vector A? How are we going to get? So the first thing is to get the component representation of vector A.
So I did the sine of 1 equals x over 4.
So what do you call an x? What is your
The vertical distance.
Vertical distance from where to where?
From the horizontal plane to
Right here? So maybe let's choose something better than x. What could we choose that's better than x for that? Because x is usually this, right?
yes.
Y. It's a better choice, okay? So you said that that's our y component of this vector. It's the part of this that's strictly heading up. So tell me again.
The
Sine of 40
equals y over 4.
So we see how, if we're doing components of these vectors, our trig is going to be really important. So we got opposite over hypotenuse. So sine of 40. Okay, you're doing good. Keep going.
And that equals 2.75.
What equals? Y does?
Y equals 2.75.
So y is 4 sine of 40. So that would be an exact representation. And then you said 2.57.
75. Or 5.75.
That would be an approximation. Okay? Somebody else. Yeah, Gage.
I think it's sine of 50 equals x over 4.
Sine of 50 equals x over 4. Okay, so you did this angle here to get that, and that's an opposite to the 50. That works. Can we use the angle 40?
Yeah, you just do cosine of 40.
Cosine of 40
X over 4.
is x over 4. And so x equals
3.07.
3.07. So exact, 4 cosine 40, approximation. Sorry, I missed it. 3.07. So now, how can we write A then? A is
3.07.
component form. So now we got A both in the polar form, magnitude of 4 kilonewtons, and 40 degrees. That's the polar form. And then component form, 3.07, 2.5. So I trust that you guys can do B, so let's just write what B is here. So somebody has it. What is it? Nobody got B? Negative 1.97. Okay, looking at those numbers, why does that make sense with what 0.35?
3.47.
Why did those components make sense looking at the vector B? So why do those numbers make sense looking at the vector B?
Because it's traveling in the opposite direction.
Okay, so it's going to the left, so our x is negative. What about 1.97 versus 2? Why does that make sense that the magnitude in the x direction is 1.97 for this vector that's 2 kilonewtons?
2 would be the hypotenuse, which is
Okay, that's true. What's that? No, but I'm talking about like in terms of what this means. What this means in terms of a horizontal component of 1.97.
It has very little vertical velocity, and like based on the angle, you can tell that it's predominantly horizontal.
Right, so this force is predominantly pulling which way? Mostly pulling horizontal. And that's why most of the force, or almost all 2 kilonewtons, is in the horizontal direction. It's pulling a little bit up, not much. That's why it's less than a half a kilonewton of a vertical component. So the number should make sense. Most of the force is to the right, left, a little bit of force is up, and that's exactly what B is showing. Okay, so how do we find then the resultant force at the point of attachment there? How do we get the resultant force? There. Yeah, so it's going to be add them together. So let's represent that. I'm going to take this B vector, I'm going to move it up here, tip to tail. How did I do? Is that about the same? Okay, so if we add them together, we get a plus b. So really convenient with components because you just add the change in x and add the change in y. What do we get for x? 1 point what? 1.09, thank you. And 2.92. And so let's draw this and see if those numbers make sense. So here is our resultant. Something like that is our resultant force vector. A plus B is the same as this vector here. So does that look horrible? Yes, it looks horrible. Does it agree with the values? More up than to the right. So 2.92 up, which is this right here. That's the vertical component of that. And then 1.09 to the right. Okay, so what about the polar form of that? How do we get the polar form? So we need the magnitude of it and the angle. How can we get the magnitude of that resultant force vector? Pythagorean theorem, square root of that squared plus that squared. What about the angle? So once you have the magnitude, you can choose any one of the trig you want. The ones we have, we use tangent, right? Opposite and adjacent, if you use the 2.92 and the 1.09, you could use tangent, and then arc tangent would get you that angle. And that would be the polar form of that resultant force. Okay, thanks for a great semester. Watch announcements and email for all the details coming up. No, it is the same as the syllabus. It's not the same as the final exam schedule for ASU. Tuesday night at 7 p.m. That'll be everything. That'll all be in the email. What's that?
But it's not here.
BAC 316. Yeah. Sorry. That's kind of a little bit on you, too.
Well, I mean, I realized it was the same one, but
Just doesn't make any sense, right?
Hey, thanks for an awesome semester.
All right, Frank. It's great having you.
Yeah, thanks.
Did you get in the 270 course or not?
I did.